This is the fall final exam review part 2, and we're going to jump right into it. Here we go, number 68. We already started this one. It says the process of nuclear fission, and I wrote the word division. So I want you to think about fission, division. So that is why I could immediately cross out combining, because fission is splitting apart. Then you have to just think about what is splitting apart. It has nothing to do with electrons. So fission, division, that's the splitting the nucleus into smaller atoms. So choice C. Number 69 is asking us to look at, is this an example of fission or fusion? This is fission. That's because we see one large thing and it's splitting it into two smaller atoms. Okay, so this is fission. And we see the splitting. Okay, so that's what's happening there. That's how I know. The next one says this picture, and explains that this is the reaction which occurs in our sun. Okay, two hydrogen atoms combining. So you could actually answer this without looking at the picture because it says this word combining. So this is fusion. Fusion is combining. Fission, you want to think division. So we see two atoms combining. So it's actually the combining of atomic nuclei. All right, let's keep going. So on this one, on our balancing, I'm going to get out my foldable. And if you don't have one of these, you may want to look back on the unit 2. You don't need it for final, but it's super helpful just because it has it all in one place. So here's my foldable. And I can do it without the foldable too, but let's look at this. So remember, in chemistry, we always turn our arrows into equal signs. So what I have on the left is equal to what is on the right. So on the left, I've got, for my mass, it says 244. So I also need 244 on this side. So I only have 240. So you want to think to yourself, what plus 240 gives you 244? And that is, of course, 4. You can check that, right? 4 plus 240 is equal to 244. We're going to do the same thing on the other side. For the number of protons, I've got 94. That means I also need 94 total on this side. So far I only have 92. So you think to yourself, I don't like saying solve for x because it kind of makes students upset, right? But that's what we're doing essentially. You're solving for x. So 2 plus 92 is equal to 94. Okay? The part where you have to pay attention is that, and this is where the foldable can help, you need to be able to identify what symbols goes with that. On this foldable, I can see that that's helium, but there are only a few that you have to know. Really just these two for these equations. So that's going to be an HE right here. Okay, let's do one where it is a beta, so I'm going to do number 73. Alright, so these ones are a little bit different, but again, same process. We want to treat it like an equal sign, so what we have on the left and the right side need to be equal. I'm going to start with my mass, so this one says 11 plus 0. What is 11 plus 0? That's 11, of course. Okay, then we want to be thinking about what is 6 plus a negative 1. You want both sides to be equal. So it's a little different, right, because of this negative 1, but still very, very doable. So that is 6 plus negative 1 is 5. Now, we have to be careful, because if you change this number on the bottom, your protons, you are changing the element itself. Okay, so this is not carbon anymore, because carbon by definition has protons. That's what makes carbon carbon. Carbon's got 6 protons. So we want to change and make sure we change our symbol to boron, because boron has 5. So I'm going to put a symbol B right there. B for boron. All right, let's do number 76. In the equation below, what does the symbol X represent? So really we're just doing the exact same thing as we were doing before. It's just kind of worded a little differently. Okay, so I'm going to say to myself, I need to figure out what went here. So this is an alpha, but I know that I have to get to 154. I only have 4 so far. So you have to think to yourself, what plus 4 is equal to 154? And that would be 150. So I'm going to just write it off to the side over here, 150. And then I want to do the same thing on the bottom, saying something plus 2 is equal to 61. So really that's just quick little math. So you're going to say basically 61 minus 2, and that will give me the number of protons, 61 minus 2, because each side is equal. And that is equal to 59. And you can check that, right? So you can think to yourself, okay, 4 plus 150, that is 154. 59 plus 2, that is equal to 61. And the thing I have to watch again is that if I change my protons, which I did here, I need to change the element itself. So I need to get my periodic table out, and I need to find number 59. Okay, there it is. It's PR. So I'm just going to find that answer choice, which is C. Okay. Next few problems. It's saying classify the following as physical or chemical changes. I do want to just quickly talk to y'all about a few of these, and I actually put it on my, remember how I made a little, I said always doing brain dumps is a great idea. On one of my brain dumps that another version, I put something about physical and chemical changes. Physical changes are reversible. That's why I have these arrows. So anything such as dissolving or changing the states of matter, that's always going to be a physical change. So right away, dissolving, and these tend to be the ones students forget about, that's a physical change. And things like condensing or evaporating, these are physical changes because they're reversible. Others, if they're not reversible, such as milk souring, you can't undo that. So on here, I wrote like a color change. So if it's changeable or it's not a reversible change, then it's a chemical change. Like a chemical change, I can't reverse it once my banana becomes rotten. It's not going to get unrotten. Okay? Burning is another chemical change. Once your wick burns, it's ash. So I will let you finish the last couple of those, but I did want to point out that for physical changes, you want to be thinking these are reversible. Okay, so if you can go back to the way it was before, that's a physical change. And the ones that students forget about tend to be dissolving and states of matter. Those are physical changes. All right, next page. Okay, so we're going to go to number 79. And again, on my little brain dump that I wrote intensive equals in common. Okay, so in common, or I also can say independent. My other trick that I actually want to add to this is I'm going to write it extensive is equal to extras. Extensive is equal to extras. So that helps me remember. So malleability, melting point, and color. Intensive equals in common. So I can have, like if I have paper clips, no matter if I have one paper clip or a whole bunch, okay, they're all going to be malleable, they're all going to have the same melting point, and they're all going to be the same color. So that is a physical intensive property. Chemical, there is no such thing as chemical intensive or extensive. Those are only physical properties. So the one that changes when more material is added, remember how I wrote on here, extensive equals extras. So what would change? Is my mass the same between one paper clip or all these paper clips? No. If I add extras, okay, if I add those extras, it's extensive. If you add more material, that's an extensive property. So here are some common ones. Mass, okay, that's one. Volume, width, height, and we'll say weight. Basically things you want to be thinking about. If you add extras, it'll change the number on like a scale or a ruler. Very few properties are extensive. Most are intensive, okay? All right. So I'm going to do number 84. It says a sample of gold has a definite volume but changes shape. It is most likely in, so if it has a definite volume but changes shape, that would be a liquid. For that, I want you to think about like a milk container. So you know how they sometimes come in those like cylindrical gallons or more of the rectangular shapes. It's still a gallon, right? So it can change shape but has a definite volume. Okay, I'm going to skip the lab safety because I think a lot of this is pretty much common sense. And we're going to go on to the part about ionic compounds. So here we go. Metals tend to lose their electrons, forming, okay, you want to think about what is their ion? And I wrote on here, I wrote my little cats lose lives. So they form positive, think about a little cat paw, or you can think about like the plus size. So they form positive ions called cations. Nonmetals tend to gain electrons, forming negative ions called anions. In an ionic bond, electrons are transferred from a metal to a nonmetal, creating oppositely charged, and that would be ions. So an ion is just the general term for the gain or loss of an electron. Another term for the charge of an ion is the oxidation state. So those are all those little numbers that we asked you to write down. These are the oxidation state. It's the same thing as charges. Okay. Let's keep going. And we'll go do a few in 92. I'm going to do some of the more challenging ones. I'll also throw in one of the simpler ones so you can see. Okay, so this first one, first thing you want to look, your step 0, is to think, is this a metal or not? Because if it's a metal, you're going to use the ionic system of naming, okay? And if you still have your foldable, that's helpful for this section, ionic versus covalent. Okay, so step 0, think to yourself, is it a metal? Okay, these all have to be metals, but sometimes on your test they might be all mixed up. So if it is a metal, you first need to think, okay, does it require a Roman numeral? Once again, use your little sheet. If it's in this sheet where I colored, the green section, all of these are transition metals that need Roman numerals in their name. Copper is one of those types of metals. The copper will need a Roman numeral. So this is copper. And don't forget, where does that Roman numeral come from? It's always going to come from the anion. So most of the time, you can just use the little number behind it. There are a few exceptions to that. But in this case, that works because then I'm going to look. You can always make sure. So this is nitrates, this NO3, and nitrate actually has a -1 charge. Okay, so a -1. So if this copper was a +2, and so I'm going to name it copper 2 nitrate. And that came from my polyatomic list. Okay, I don't need to memorize those. You just need to have that polyatomic list handy and ready to go. Okay, let's do this one. Once again, iron. Iron, you want to think, where is this? Does this need a Roman numeral? It sure does. It's in the pink section. So look to your non-metal to get the Roman numeral. That would be iron 3 oxide. And actually, I said I was going to do this one, but I think I want to do one of my exceptions because not everything needs a Roman numeral. Okay, aluminum is in the exception block, meaning it has a set charge. It does not need a Roman numeral in its name. So things in this red section do not need Roman numerals. Okay, so I'm just going to name this one aluminum sulfide. Put that IDE ending. Okay, now I'm going to write my formulas. Once again, you want to make sure, because they're probably going to be mixed up in your test, these ones happen to all be ionic, but that's a 4-step formula. Okay, 4-step formula. And we'll try this one right here, iron 3 sulfates. So step 1, write out your symbols. Step 2 is charges, but I'll do it one step at a time. So sulfate, that is not sulfide, that is sulfate. So if it ends in ATE or if it ends in ITE, you want to be thinking, I need to look at polyatomic list. Copy it straight from there. So that is SO4 with a -2 charge. And then my iron, you might be wondering, oh, what's my charge? Don't just say, oh, it's iron 8. Nope. You want to use the Roman numeral. If it's in this transition metal area, okay, or here it's a little more clear, the green. Don't guess. Use the Roman numeral. This is iron 3. Then we need a crisscross. So the 3 will come over here, the 2 will go over there. Okay. We'll do one more. We're going to do aluminum sulfide. Okay, so step 1, symbols, AL. And then this is sulfide. It is not sulfite or sulfate. So I just want to use an S. If it's just IDE, you want to use just the element all by itself in the periodic table. So step 2 is charges. Aluminum does have a charge because it is in the exception block. And this must have gotten wet. But this should say +3. Aluminum is a +3 charge. It is set. Sulfur has a -2 charge. There's sulfur. They crisscross. And then I'm all done. I don't need to reduce this one. If you can reduce it without making a fraction, you need to. and that just means, well, maybe we should do one example where I do need to erase. Let's say, I wonder if they're on. Yeah, there is an example in here of one that, there aren't any on here that need to be reduced. We'll probably find one later. So let's keep going to the mole. This section, the mole. How many particles that can be an atom, molecule, or formula unit are in a mole? So if your question says how many atoms are in this, how many molecules, and it says the word mole, the answer is always going to be 6.02 times 10 to the 23rd. Always, every single time. This number is called Avogadro's number. Okay, now if your question says what is the molar mass, that is not this. The molar mass comes from the periodic table. So this one says molar mass. It's asking me for the molar mass of protein. So I'm going to look on there, and that says 79.904. Okay, so now I'm going to show you how to calculate molar mass. This one says calcium phosphate. So first you have to figure out the formula. Okay, you have to figure out the formula. So it's a 4-step formula. Step 1, symbols. So Ca, and this is phosphate, ATE, phosphate, PO4, with a -3 charge. And my charge for calcium is +2. Then they crisscross. So the 3 is going to come over here, and the 2 is going to go over there. And I wrote a 3, but that's a 2. 2. Okay, so now here's my work. I want to say 3 times the mass of the calcium, because I have 3 calciums. So I'm going to find the mass, and that is 40.078 plus, again, I want to do the same thing on this side. So now I'm going to do that for the phosphorus. I have 2 phosphorus because this 2 will go to the phosphorus, but not the calcium. Can't leave the parentheses. So 2 times the weight of the phosphorus, which is 30.974, plus, in another parentheses, I have 8, because 2 times 4 is 8, 8 oxygen. So 8 times the mass of oxygen, which is 15.999. Now, I like to do it all in one step using parentheses because I think it reduces the chances that you will make mistakes. But you have to use the parentheses, otherwise it will mess up your order of operations. So I'm going to plug that all in. 3. Okay, see how I plug that all in? I use parentheses the whole way, so I don't come up with an issue with order of operations. Okay, and that is equal to 310.174 is my final answer. And that is grams per mole is my unit. Okay. And then I'm going to do one more of these. How many atoms are in 1 mole of neon? That's just like we talked about before. 602 times 10 to the 23rd. So if it says how many atoms, you can just use Avogadro's number. Molar mass, like these next two, you need to look at the periodic table and possibly, like on this one, do what we did up in this problem. Okay? Now we're going to move on to covalence. So covalent bonds occur between two nonmetals. So covalent bonds are basically only involving everything in this section right over here. Okay? In this type of bond, electrons are shared. Ionic bonds, on the other hand, we already talked about that, form between a metal and a nonmetal. And in this type of bond, electrons are transferred. Oh, and there's all that. Again, if you have this foldable, it's helpful. It's very helpful because it will give you the differences between the ionic and covalent. Okay, let's keep going. Okay, let's see. I'm going to start with 106. Which of the following sets of atoms will form an ionic bond? So for an ionic bond, remember, you're looking for a metal plus a nonmetal. Okay, so right away I can see sodium is a metal. Okay, that will form an ionic bond. And actually, I'm going to go back and say on 105, which type of compound uses prefixes? That is only covalent. And if you have that foldable, you'll have all that information ready to go for yourself. So let's do some naming. What is the name of CaCl2? Is this ionic or covalent? This is what you want to be asking yourself. Look to the first one. That first one is a metal. You need to use the ionic system, which we just went over. No prefixes, so take out that garbage. Okay? No prefixes. Okay? The next thing you want to think about is, does it need a Roman numeral? It is not in the green section. Calcium is right here. No Roman numeral. I'm going to cross that one off too. Then I just have to decide, is it chlorate or chloride? Remember, if it's chlorate, we would see as ClO3. So it's just chloride. B. Now let's do number 108. It says, what is the name of Cl2O5? Okay, is chlorine a metal? No, it is not. That means we are going to use those prefixes. Okay, so what you see is what you get. There's no swapping and dropping. So I'm just going to say the prefix for 2 is di. So di should be in the front. Dichlorine. The prefix for 5 is penta, but with oxygen we usually drop the A. So this is dichlorine pentoxide. Okay, let's keep going. I'm going to go to this one. So F. Is this a metal? That is fluorine. It is not a metal. So once again, I'm going to use my covalent naming system. Okay. And here there are 3 of them. So this is going to be trifluorine dioxide. Okay. So be careful. Look to the first one. Decide if it's a metal or not. If it's a metal, you should not have prefixes anywhere in there. Okay? Let's do some formula writing. And these could be mixed. It could be ionic or covalent. And that's what you'll see in your test. We're not going to necessarily tell you. So you need to think about that because they have different formulas. So, diphosphorus. Right away, I'm seeing prefixes, so I know this is covalent. I'm going to use the covalent formula writing system, which is just what you see is what you get. So I'm going to write my symbol. Then I'm going to write the prefix for di, which is 2. Okay. Then I see trioxide, so I'm going to write an O and then a 3. Very simple. But we got to be careful. We can't just do that for all of them because barium, for example, is a metal. Barium's a metal. So on this one, we write barium. And then we have to think, does it need a Roman numeral? It's not in the green section. Barium's right here. So why did I write the full name? I'm doing a little more than I need to. I just need to write the symbols. 4-step formula. Ba, barium. It's got a +2 as my charge, +2. Then I'm going to do chlorates. It's not chloride, so you should be thinking, oh, this is a polyatomic ion. So that is chlorate, ClO3, ClO3 with a -1 charge. ClO3 with a -1 charge. These you have to crisscross. So crisscross, that 1's going to come over here. The 2 is going to go over there. When they crisscross, we don't bring down the plus and minus. So it is BaClO3. Okay. And then we'll do a little bit of, we'll do 2 more of these and then we'll go to name. Okay, we'll do a few names as well. Okay, dihydrogen dioxide. So this is covalent because I see the prefixes. So H2O2. Okay, di and di. This one though, this is covalent. That is because I see iron. Iron is metal. So step 1, symbols. O. Step 2 is charges. My charge on this one I get from the Roman numeral. There's a Roman numeral. You use that as a charge always. Okay, my charge on oxygen is -2. Once again, have those oxidation numbers written down for yourself. -2. They crisscross. And then we do have to reduce in this case. So unlike this one where we wouldn't reduce because we do not reduce covalent compounds, ionic compounds must be reduced. So I'm going to reduce it. 2 divided by 2 is 1. So this would just be FeO at the end. You can leave the ones there, but typically in chemistry you are not going to see a subscript of 1. Coefficient of 1, yes. Subscripts, no. We don't usually write coefficients. Or we don't usually write subscripts, rather. So there's your final answer. Okay, on the next ones, we're going to do some naming. This is a metal, so I want to use my ionic naming system. Again, there's a metal there. A metal at the first one, you only have to look at the first one. You need to use the ionic naming system. So magnesium. Magnesium does not need a Roman numeral because it is in the first group. Chloride. All right, let's look at this one. Nitrogen, I'm going to look at that. Is that a metal? No. So I'm going to use my covalent naming system. That needs prefixes. So I say di, nitrogen, di, or no, so this one's 5. Pent, pentus, pent is 5. Pentoxide. Pentoxide. Okay, and I'm going to do this one just because a lot of students forget what 6 and 7 are. So if you need a prefix review, here they are. So this is hexaphosphorus, and heptoxide. Normally we would say hepta, but A and O don't work correctly in English, so heptoxide. All right, let's keep going. Next page. And this is our very last page that we are going to do here. So great job. When correctly balanced, the coefficients are, so we just did this, you just took a test on this, so hopefully balancing is very fresh on your mind. So it's just asking you to get the coefficients. So some of you like the ping pong method, some of you like the guess and check. I'm going to do the guess and check. I'm just going to look here, what's not balanced. I immediately see my bromines. I've got 2 on the left, but I've got 3 on the right. So that is not balanced. So I can balance that No problem. No problem. I just need to think, what is the thing that I can multiply them by on each side to make them the same number? And I want them both to be 6 because 2 times 3 is 6. So I want to make sure I have a coefficient in front that will allow each side to have a 6. So here I'm going to put, right here I'm going to put a 3 because 3 times 2 is 6. And right here I'm going to put a 2 because 2 times 3 is 6. So now I have 6 bromines on each side, right? I have 6 bromines on each side, but I also need to fix my aluminums now because on the right side now I have 2 aluminums, but on the left I only have 1. So I'm going to put a coefficient of 2. So my correct coefficients are going to be 2, 3, and 2. That's choice B. Okay, let's keep going. I like 117. It says, in the combustion reaction of methane, what are the products that always in a combustion reaction, you're going to have H2O and CO2 every single time, no matter what. If it's a combustion reaction, that's always going to be it. All right, let's identify some reaction types. So I see one single compound at the beginning, and then my product is 2 individual elements. That is a decomposition reaction. Oh, I see CO2 and H2O, what we just talked about there. That's a combustion. On this next one, I see 2 single elements coming together, and as my product, I have a compound. So the opposite of decomposition, which is synthesis. Right here, I've got iron and sulfur together, and I've got hydrogen and chlorine, and it looks like they just switched partners. This is different than a single replacement because nobody's left alone. Okay, that's a double replacement. So for double replacements, you're looking for 2 compounds on each side, neither of which are CO2 and H2O, because you're more like combustion. Okay, so I'm going to skip down and find a single replacement reaction. So in this one, it's different than a double replacement because you see nobody's left alone. Here we've got somebody who's alone at the end. That's the calcium. So we have the sodium came in, replace the calcium, kick the calcium out. So that's a single replacement reaction. Okay, so I'm going to balance on 121. I'm going to balance these because I want to talk to you about polyatomic ions, because students sometimes struggle with the polyatomic ions, but I have good news. It's very easy with polyatomic ions, and I will even write the little table method because some students like them. So CS2, CS, and guess what? Don't break apart your polyatomic ions. I don't need to separately balance sulfur and oxygen. I can just treat it like a single unit. So I'm going to just count what I have on the left and what I have on the right. On the left side, I've got 1 Mg. I've got 2 cesiums. And I have 1 SO4. Now I'm going to look on the other side. I have 1 Mg on the product side. I have 1 cesium. And I have 1 SO4. So I'm going to look at my columns and see the only thing I can see so far that is not balanced is the cesium. This was a very easy one to balance. So I'm going to put a 2 there. So now my cesiums, I have 2. And everything else is already balanced. So I just need to put a coefficient of 1. And then I'm finished. This is a single replacement reaction. Okay? Single replacement. And now I'm going to do this very last one. And it says, what is the mass of the last flask? So I love these because your products and reactants are equal. So even though I don't know what this is, since I have both of them on this side, all I have to do is add 102.3 plus 16, because it's the law of conservation of mass, and that is 118.3. So that's what this has to be. Law of conservation of mass. All right, I'm going to let you finish the rest of these on your own. Please be asking questions and working hard, studying hard. Remember, if you do this entire review, you get to use it on your final, and it will really help you because the final should be very similar. Good luck!